This is the second module of thermodynamics, and we will now start the third subtopic, which is thermodynamics of reacting systems. So, what do we mean by this? But so far everything we have learned in the first part of thermodynamics, which was dealing with pure substance, the laws and the applications, in all of these there were no chemical reactions. We had one type of a molecule, and no matter what we did to that at the molecule level or at the macro level as a system, heating, cooling, work output, input, heat transfer, input, output, that species remained the same. We then looked at in the second part, what we looked at was mixtures. And in that we said we will focus on gas mixtures, and we developed a general approach to say if there are two gases which are mixed, how do we get the properties of that, and then how do we use that in the laws to analyze systems for heat and work transfer. Again, there also we said no chemical reactions. The only thing here we had though was that in some cases of a pure substance, we had phase change. So, solid, liquid, vapor phase change was there, but when phase change takes place, there is no chemical reaction taking place. It is the same molecule that goes from one phase to the other phase. Now, we are saying that look, we are going to look at mixtures, and we will particularly concentrate on gas mixtures, although the theory we develop later on will be good for liquids and solids as well. So, now we will say that we have a gas mixture, and later on we will look at liquid and solid, where the two constituents, say A and constituent B. So, this was two component system, I equal to 1, I equal to 2, binary mixture, and now we say we will do something and let A and B react. So, there is a chemical reaction between A and B, and it ends up producing an entirely different set of molecules, which we will call say C and D. So, what we had was we started off with a particular type of a mixture, we had a chemical reaction, and we came up into a final state which is another set of molecules. So, this was the initial state where we had two types of molecules, and after the chemical reaction what we call as a final state, we have two other types of molecules and maybe something else also. But the difference is this, that in both cases we are assuming that the initial state was a thermodynamic equilibrium, but during the reaction process there was no thermodynamic equilibrium. The next thing that we are worried about is that when this thing happens, there would be energy transfer, and that is what is of importance to us, besides of course the fact as to maybe the objective is to produce C or to produce D or to minimize something else. So, let us now define our scope of what we are going to do in reacting systems, and to do that we will say that we are going to study this type of a reaction that I just put out, and we say that you have two different type of molecules which you must have minimum 2 to make a reaction possible. We could have 3, 4, 5, and there will be a minimum of 2 products that are coming out, without which you cannot complete the picture. So, we can say that products are C and D and reactants are A and B. So, we got two now categorizations taking place. This we, as you just saw, this is the initial state or state 1, this is the final state which is state 2. And we are saying that A and B molecules react to produce C and D molecules, and in what numbers they are there is what we put up here as the number of moles of each one of them, nu A, nu B, and produce nu C and nu D. We are assuming that the numbers here are such that all of A and B disappear and C and D appear. As we shall see later, this need not always be the case. This mixture is what we will call reactants, and we will denote it by the R, and what you have here are the products, and this we will call P. And during this chemical reaction, something else also happens, which is Q, energy release or energy absorption. So, during this process, which is technically here, there could be energy input or output, and this is Q, and in the way we write equations, we put this Q on the product side and say plus minus Q. So, this is what we want to study, and in general this is what is the reacting system, where A and B could be anything. There are so many industrial processes where A and B could be very different types of molecules, and the objective is to produce something else. That is, in general, this is the starting point of what we all do in chemical engineering. When this type of a system happens, many questions will pop up. So, we are going to list out some of those questions, and first we say, and of course, we are drawing on our knowledge of what we have already learnt in thermodynamics, and the first question is, was this a closed system or an open system? The equation by itself does not tell us anything. So, we will have to factor that in. The second is, when this went here, did this reaction happen very slowly or was it fast? Or a third case, was it spontaneous or instantaneous? What we are meaning is that there could be a very slow chemical reaction, or instantaneous could be something like an explosion, that within a few microseconds the reaction is over. Then we have put an arrow here saying that everything is becoming like this. Well, technically, is this correct? That if we do cause a reaction and finally we come to an equilibrium state, or there was an equilibrium here and an equilibrium there, is it true that in this reactants there were only two molecules and the product only these two molecules? The counter question is, when this was in equilibrium, was there some C and D in it, or in the products when there was C and D, were there any amounts of A and B in it? And the answer is that yes, this will always be the case, and so these reactions are always to be indicated by a two-way reaction. That every time a reaction is going forward, there is also a backward reaction taking place. We will later come to see how from kinetic theory of gases we can look at that, and why even at equilibrium it does not mean it is a static equilibrium, but it is a dynamic equilibrium where all these reactions are still always taking place. So, what we have here is a forward reaction and a reverse reaction. So, we have to worry about both reactions when we want to look at a complete picture. And that is the question we were asking, whether the reactants were all R only or the products were all P only, or were they mix of C and D and maybe something else also. The second thing is, we have somewhat clearly specified what is the starting state, which is your initial state, state number 1, and the end state, which is the final state, which is state 2. So, once you know that this is my initial state, this is the final state, then we can begin to apply the laws of thermodynamics to do the calculations like we did for a single pure substance. Then this reaction does not tell us if there were any other materials there or substances. For instance, if we have this reaction that we have written, nu A and nu B of B molecule on this side, and on the other side we have nu C of C plus nu D of D. And now we will say that this reaction went both ways. Well, was there any other chemical here, say some other chemical, say X molecule, which was inert? It did not react with, did not participate in it, but maybe it affected the rate and the way the chemical reaction took place. Or was there something else here, like a catalyst, that made it happen? That also we haven't said there. Then we raise a very fundamental question about all reactions. What the way we write this and the way we have been taught, we are basically saying that if I put these two molecules in a control volume, so this is one molecule and we put into this the second one, then does it happen that they just come, do some collisions, and straight away the end product is this? So, does it mean that one A molecule hits another B molecule and what we get is C and D? Does this happen? In just one collision this happens, and this collision we are talking because this is all in a gas phase, or we call it a vapor phase. If this were to happen, we would call this what is called a single step reaction. Well, in reality, no chemical reaction is a single step reaction, and we will see from this thing, which is the kinetic theory of gases, why that is the case. So, that is another aspect that this equation does not tell us. Then we ask the question, where and under what conditions does it happen? So, we are basically saying what is the physical domain in which the chemical reaction takes place. So, you may have a big domain, but the reaction is confined to a very small space within that domain. What is that domain? And then we ask, well, after the reaction has happened and equilibrium is reached, at what point do we say that we have equilibrium? Do we wait for a long time? Does it happen very quickly? And so, once equilibrium has been reached, what is the composition at the end? And then there is always the basic thing that we are all looking for, is the energy aspect of this reaction, where we have the most simple thing to ask is, was this an exothermic reaction or was it endothermic? There are many types of reactions which require heat to be supplied. There are many others where heat is given out. So, that is the exothermic reaction. And finally, yet another question we can ask, is this a controlled reaction or is it uncontrolled? So, basically we are asking here, when we say it is controlled or uncontrolled, is that did we design the reaction to happen in a particular way. So, we can control the parameters, make it happen faster, slower, increase the quantity, decrease the quantity or what. Or is it uncontrolled, where once it starts there is nothing one can do, it just goes its own way completely. And then there are other aspects we can add to it. Well, can I interfere and stop this reaction? For example, I want to stop it, and this is exactly what we would like to do when you have a fire and you want to stop it. So, the fire is nothing but again you got a lot of chemical reactions taking place, and now you are asking the question, what should I do to stop that chemical reaction? So, these are some of the questions that are coming up by writing a very simple thing, a reaction like this, which we have already come across many times. So, this takes us to a very complex set of issues which are addressed in advanced courses in combustion. We will not go into many of these aspects here, but we will constrain ourselves to asking in one particular type of reactions, which is combustion reactions, and that too we will say what is the relation between properties of these molecules and the energy that is released. So, we are only going to be taking a macroscopic approach to asking these very few questions of a particular type of a chemical reaction. So, our focus is going to be on combustion. What it is a subset of a reacting system, and it is characterized by the fact that there is an oxidant, or it is the oxidation of a fuel by an oxidizer, which could be usually air, but could be something else as well, in an exothermic reaction. So, we can say along with energy or heat release. This is what we are saying is combustion, and this could be, when we say this is combustion, we usually imply that this is a controlled reaction. So, we are actively designing a system to make some reactions happen in a particular way, in a particular space, at a particular speed. So, that is what tells us that what is it that we want to know about these type of a system. So, in the study of combustion, we have to first begin by looking at two things. One is fuel and the other is oxidizer. And we say that in general, if you look at the state, the fuels could be gaseous, or we can even say that this is a vapor, or they could be in liquid phase or in solid phase. Any of these can be there. And the question is, what do we mean by saying that there is something called a fuel? So, what is this fundamental idea of what is fuel? The implication is that we are saying that this is any material which when burnt will release heat. So, is there any restriction on what do we mean by the word material or a substance? Well, technically anything and everything will burn, or which means that it will get oxidized if you have all the right conditions. For example, the common fuels like say gas, oils and say wood and coal, those are quite understandable, but the fact is that yes, even metals like say aluminum or things like say potassium, chromium, at the right state they also burn, and they are used in many applications. An example of this is your firecrackers and pyrotechnics that we see. So, all the colors that we get, it is coming out because there is a combustion reaction taking place with different elements, and each element gives out a particular type of a color. So, we are saying that in general fuel is anything that can be burnt in air or oxygen or in some other case. So, the other part is this was the fuel. Well, what about the oxidizer? The most common oxidizer is what we have around is air, and air, as we have already seen, is O2 plus 3.76 N2, and the important thing now is that we do not treat air as a pseudo pure substance. So, in the first part of thermodynamics, which was properties of a pure substance, we said that this is a pseudo pure substance. Even when we were looking at mixtures of air, which is dry air and water vapor, again we treated air as a pseudo pure substance. Now, when we are looking at reacting systems, we will no longer treat air as a pseudo pure substance and treat it as a mixture of O2 plus 3.76 N2. So, this is one major change that we are now making from what we have learned so far. The other oxidant that is quite often seen is pure oxygen, O2. And this is used in many cases like, say, welding, where you have a fuel and oxygen being burned to produce a high temperature, and then we burn that. And then there are very special applications where fuels could be something else, like potassium perchlorate or ammonium perchlorate. Or it could be even some other molecules. And these are characterized by the fact that in a molecule like this, there are 4 atoms of oxygen. So, which means that if you can somehow get this oxygen out, this becomes a fuel. So, things like this, when mixed with some sort of a fuel, which could be, say, very fine aluminum powder, and then when ignited could burn, and so you have a chemical reaction of Al plus O2, and you can balance this, basically producing Al2O3 plus a large amount of energy is released. So, the aluminum becomes the fuel, but the oxidizer, although it was oxygen, came from a chemical like this one. And the reason I cited this is that that is what you would see in solid rocket motors of launch vehicles and missiles. So, that is the place where we get the oxygen and the oxidizer from. So, even in air, when we talk of combustion with air, it is actually the active part of air which takes part in the chemical reaction is this O2, and in this course for now we will treat N2 as inert, but inert in the sense that it is chemically inert, but when it comes to energy it does participate, and we will see that as we go along in this lectures. So, now before going into the thermodynamics of it, let us look at some applications and try to figure out what is it that is actually happening and how we can pick out the system that we are looking at and apply the thermodynamics that we are learning here. At the same time, we will also see what are the limits of what we are learning. So, let us start by looking at the gaseous fuels and the process of combustion or burning of a gaseous fuel. So, what we have is some examples here. This could be piped natural gas or compressed natural gas, or one can even call this NG, which is largely well over 95% is methane. The next other fuel that we have, what is burnt in the gaseous phase, is LPG, which predominantly is C4H10, but actually this is both of these, they are obtained from crude oil after a bunch of processes, and so they are never 100% pure substances, but they have smaller amounts of many other chemicals with them. For our purpose, we will just say, okay, this is methane and LPG is butane. Then there is biogas, which is the gas that you get when you do digestion of waste, and this is nothing but 50% CO2 plus 50% CH4. So, it is a very large amount of carbon dioxide in it, and the methane that is coming out, this becomes the fuel part of it. CO2 of course is chemically not participating, but yes, in the energy balance it does come in. So, let us take an example, some examples and see what happens. The first example I have cited here is a cook stove, or you can even look at the Bunsen burner, where the gas being burnt is either methane or here it could be LPG. So, here is a sketch of what is happening in our domestic LPG stoves. The fuel is injected from here. This is the tube into which the fuel comes, and it does not matter whether it is LPG or whether it is CH4. The fuel comes out here with a high velocity, creates a low pressure, which in turn sucks in surrounding air, forms a mixture of the fuel and air. It comes into this bottom chamber, and through small holes in this ring, there are many of them in a circular manner, we see that a flame sits over there. But remember that if we just put it on and do nothing, there is no flame. So, we have a lighter or a matchstick that we put to it, and that sets up a flame. So, that is something we did, that by itself the reaction did not start, we had to do something to ignite it. Basically, ignition means that you have to give certain energy to initiate the chemical reaction. Once the reaction stabilizes, it is self-sustaining. Then you do not need to give ignition again and again. And it is an issue in terms of safety also, that if we try to ignite it and it does not ignite, and the gas still continues to flow, gas air mixture continues to flow, then you could have a potentially a dangerous situation, where if at some point there is a ignition taking place, you could have this whole thing burning very fast, causing an explosion. So, what is happening here is that this mixture went in, and if there was no flame there, this mixture would have just gone out and flown out like that. In the particular case, methane is lighter than air, it goes up. If it were LPG, it would slowly start coming and settling down towards the floor. It is heavier than air. Now that there is a flame, the same thing is happening, that the reactants are going in, they go through the flame and they come out. So, what you have is a thing which is called the flame, which is that part of the domain where the chemical reactions are taking place. That is what the part, and usually we associate that with the visible part of it. There is a visible flame, and then there is an invisible part of the flame. Visible flame is where you get light, which is where the chemical reaction is taking place. So, this is what is happening, and what we see typically in this case is mostly you get a blue and whitish type of a flame, and when we put vessels on it, we do not see any deposit happening. That means there was no smoke being produced, which smoke is nothing but carbon particles. So, if the holes are open, this is what will happen. But if somehow these holes get clogged or are completely shut, air is not coming in, then it comes in and you start seeing yellowish colors coming in. And this is something we can do in the Bunsen burner, where at the base of the burner there is an opening, and that opening is, if the opening is open, air is coming in, you have a, what you are coming into this is methane plus air, which is got the oxygen, and so it forms a small flame, bluish white in color, and that is where the combustion is taking place. These gases come, go through this. In the process, the temperature of this gas goes up, its composition changes, and that is where the energy came from the release. Now, if the air port were to be closed, something else happens. You would have seen that this flame becomes very big, becomes much bigger, and it changes its color from a small bluish white flame to becoming a yellowish flame, and you can see at the top smoke that is coming out, which is particles of various carbon. So, here we have come across two new things. One, when it was a small flame here and here, which was bluish white, this was produced when oxygen and the fuel, they were together. This is called a premixed flame. And the second case, when only the fuel came, then it, because there was inside there's all fuel, no air, outside it is all air, no fuel, no reactions take place there. It forms a region there where mixing is taking place, and because of that there is a chemical reaction taking place over there. It forms a yellowish flame, and so here air has to diffuse into the fuel, or the fuel has to diffuse into the air, and this is what is called a diffusion flame. So, we have introduced two new things, but one, what is the type of the flame, what is called pre-mixed, and the other one is a diffusion flame. So, this is one important thing that has come out. Now, let us see some other ways in which we can burn a gaseous fuel. So, what happens in a furnace or in an oven. So, what one does there is that we have a supply of the fuel coming in, which is say this pipe, and separately there is another supply of air, and this is the fuel. And this is a steady process, we are continuously throwing into it, and what happens is this whole thing mixes and it ends up forming a flame. So, what we have done is we have mixed it, tried to get as good a mixing as possible and produce pre-mixed flame, or else we end up producing a diffusion flame. A third application is an internal combustion engine, particularly a spark ignition engine, where what we have done is, say the piston is at the end of the compression stroke. Inside this, what we have is a mixture of air plus the fuel. Fuel is in gas or vapor phase, and then with a spark plug we do the ignition, and what we have is combustion taking place. So, what it does is that because we release the energy here, the reaction first starts here and then it produces more energy. This causes the reaction to now be there, and this keeps going forward, and you have a situation where the flame is moving forward. Behind the flame are the products, ahead of the flame are the reactants. So, that is what happens in a spark ignition engine. What could be other possibilities of burning it? And one is that if you have a room in which say the gas has been leaking for some time and there was air, and at this point there is an ignition source here, then again the same thing happens what you saw happening with the engine, where the spark took place, immediately the flame spreads like this. The rate at which this flame goes is very fast, and what you have is an explosion. So, this was uncontrolled explosion, which we did not want, that is why we call it uncontrolled. In a spark ignition engine, we were controlling that explosion, and in the other cases like your LPG burner, we do not want an explosion. Another example is welding and brazing, where what one does is that we have the same idea, that you have gas fuel coming in, which is typically C4H10, and around that we are putting in typically pure oxygen, and then we produce various types of flames that you could have seen in your workshops, that you could have a small flame, an oxidizing flame, a reducing flame, a big flame. All these are possible by adjusting the ratio of these two. The important thing here to note is that the oxidizer is pure oxygen, so the flame is much hotter. So, qualitatively we say that if O2 was there, you got a hotter flame, air is there, we did not get so hot a flame. Why? We will look at in this course. Now, let us look at liquid fuels. And what do we mean by liquid fuels? It is a whole variety of things, just like kerosene, then ATF, aviation turbine fuel, which is the fuel that is used in aircraft engines, whether it is civilian or military, does not matter. Then there is various grades of diesel oil, high speed diesel, light diesel oil, like that, and then we have petrol, and even we can even say that there is crude oil or heavy oil, or it's also called fuel oil or furnace oil, which is pretty much like crude oil but slightly cleaner. And then there could be other types of oils, including say things like vegetable oils. We can approximate these by much heavier hydrocarbons, typically starting with C4, say butane. Then there could be hexane, heptanes, octanes, decane, dodecane, and heavier hydrocarbons. So these hydrocarbons are the ones that exist in the liquid phase in ambient pressure and temperature conditions. So there are many applications where this is used, and we start by looking at the kerosene cook stove. So what happens in this is there's the wick type of a kerosene cook stove. There is a tube which carries in it a wick which is dipped at the bottom in a kerosene tank. So we have here at the bottom you have a kerosene tank in which the fuel is put there. So the fuel is here. The wick is nothing but a sort of a fabric, artificial or man-made, which is porous, and because of that this fuel is sucked up by capillary action into this. And if you do nothing, then this kerosene will keep evaporating from there and nothing will happen. But if we light it up with a matchstick, and the construction of the stove is such that outside there is a cage through which air can come in, then at the top one can see a nice stable flame being produced by this. And if this is clean and lot of air is coming in, we see pretty much a blue flame that is produced by this type of a wick stove. And on top of that we put all our pans and pots, and that's where the cooking takes place. So what is happening here is that we got the liquid coming up, and then at the tip of the wick this thing kept getting energy from the flame which was already there. It vaporized, so the liquid fuel first became a vapor. This vapor then mixed with air, and then we had the flame being produced. So the additional thing that has happened in the case of a liquid fuel is this part of the process, the liquid becoming a vapor. So that's what is the basic idea. So this is what is one type of the kerosene cook stove does. Now let's look at something else, which is an oil lamp. So what we have done is we have taken a small pool of oil, and this is where we can say that there's oil, and we did the same thing like the kerosene stove, and what we put there was a wick. So this is the wick sitting here. This could be made of cotton or something else. Again, this is there because it is porous. This gets soaked with oil, oil comes up to here, then we put a matchstick to it, ignite it, and then what we see happening is you see a flame coming there. Same thing happened. This oil vaporized, came here, and by buoyancy, because it was hot, it started rising, and because then we had put a flame to it, it started mixing with air. So there is a zone in which it mixed, and then somewhere in that zone the chemical reaction started, it burnt, and the products kept leaving the flame. So the same idea is coming up here, that first the liquid became a vapor. But the difference from the earlier application was that this vapor came only at one point, and the only way it could get air was by mixing with the ambient air by diffusion. And so, when this thing particularly burns, you always end up seeing a yellow flame. And the yellow flame is because the combustion has got, there is oil, it is not going to the full extent like it did earlier. It formed some very small soot particles which became hot, and because of that it was emitting a color which is radiation, both infrared and visible, where there is a lot of yellow wavelengths in it. So, that is why these flames, which is the diffusion flames, whether it was gas or with oil, these are yellow flames. So, this is the idea that we saw is a diffusion flame. So, that was the oil lamp. And then something that we often see happening as a mishap in the kitchen, that if you are doing some deep frying and you have put all the oil into a pan or a kadhai and you are heating it, and if by chance it gets allowed to be very hot and the flame is also very big around it, then there could be a possibility that this oil itself will catch fire. So, what is happening here again is that oil is vaporizing, mixing with the air and burning, and because this is too big, it cannot have a stable small flame like this. It burns in many places at different times. It is a very time dependent and a transient type of a flame. So, this is something we do not want to do, and as safety things, the last thing that you want to do on this is to throw water on it. Water will come on this, it is heavier than oil, it will go down, it gets hot, oils are well over 100 degrees Celsius, the water will become a vapor, the expansion of 1000 times in volume, it will splash this oil out of this and come onto your hands. So, never throw water on an oil fire. Now, let us see what happens in another important application of liquid fuel combustion. This is the internal combustion engine, which is a compression ignition engine type. So, what is happening here is that we have the cylinder, and at some point we started injecting the fuel. So, when you say we are injecting a fuel, basically what we are saying is that we have a small opening in which there is the liquid fuel, which we are injecting at a very high pressure, and because of that, when it comes out, after a while it becomes a mist of droplets of the fuel. So, this is atomization, and typical diameters of this in engines is like 100 micrometers. So, you are looking at that fine a mist of fuel. Now, what happens is, how does it burn? So, what is happening is that these fuel drops will come out, this surrounded by hot air because it got compressed. This fuel will keep vaporizing and form a cloud of vapor around the drop. This will keep moving into the air, and at some point you will start seeing mixing taking place, and we start seeing a mixture, a zone where you have a mixture of fuel plus air. And it is in this thing that because of the high temperature, it will ignite itself and it will end up forming a flame which is sitting somewhere around this drop. With that heat coming back to the drop will keep on evaporating. This flame will be there, it will gradually change its shape, and finally, when all the fuel is consumed, it will form some little particle of impurities or some charge at the end, and the flame will die out. So, each drop goes through this, and there are millions and millions of these drops every time it does it, and that is how it is burning. But the point is that here also, first it was the liquid fuel which became a vapor which mixed with the air, and then the burning took place. But the way it is burning is very different. So, this is a very simple idealization of how a single drop of a liquid fuel, when atomized, how it will burn. Another important application of where combustion takes place is the gas turbine, aircraft engines. not just for powering aeroplanes, but also for powering ships and for generating electric power. In all the cases, the process is the same, that you atomize it, but the difference is that in an engine you inject it and then you stop, and then nothing is there, and then again the next cycle again you inject it and then it stops. So, this is an intermittent process, whereas in gas turbines this is continuous. So, you have an injector through which the fuel is coming out, the liquid fuel is there, aviation turbine fuel, which is typically, that is what it is called. It is some sort of a very light version of kerosene. It comes out, the drops come out here, they gradually go out and become small, and they have a vapor cloud around them, and then they become smaller, and the vapor cloud is burning away, and at some point the combustion is complete. And because of the fact that it is a diffusion flame, these flames will be yellowish, and overall all the millions of drops which are doing this will give the appearance of a space which is called the flame. This is a continuous process. So, you are continuously injecting this and also continuously supplying air, and so the flame is produced over there. So, that is the difference between the droplet mode of combustion in an internal combustion engine and in an aircraft engine, or for that matter the same thing also happens in any industrial application where oil is being burned. So, you could have an oil fired furnace. This could be a power plant which is normally burns coal, but at low loads it also burns oil, or for ignition you use oil, or it could be a billet heating furnace which is used for heating metal before it do forging, or it could be that you are firing this for baking and many other applications. So, the main idea was that in a liquid fuel you first have to vaporize it, mix it with air, and only then it will burn. But the reaction that we wrote in the beginning, it did not tell whether it was solid or liquid or vapor, we just said it happens. Now, we are seeing it is much more complicated than that. The third type of fuel we are going to be looking at is solid fuel, and this is examples of this is wood, coal, coke, or a plastic, rubber, and even metals. So, we will take the example of the wood burning stove. So, we took the example of the gas burning stove, which is used by about 15% of the households in our country. Then we looked at the kerosene stove, which is another about 30–50% of the households use kerosene for cooking, and then the remaining large section of households still use wood or maybe cow dung or just dung cakes. So, what is happening here is that you have fuel, say a wood, which is cut into a piece, and we know that if we try to put a matchstick to it, it does not burn. If it is a very thin piece of wood, then yes, it might catch fire, but then it will not sustain, it will die very quickly. But then when you make it big, it needs a lot more heating before it catches fire. And once it catches fire, what we are seeing is going to happen is, we start seeing flame that are sitting on top of it, and you can clearly see that there is a distance between the two, and that this is a fuel vapors coming out, and then they mix with air and form this flame. So, this is a very mixed type of a thing, largely a yellow type of a flame, but in some places it could even be blue whitish. And there will be a lot of smoke, basically saying that your burning process was not very good, in the sense that everything did not become carbon dioxide and H2O, but became something else. So, what is happening is that we needed to give a lot of energy to the wood before it could start burning. So, what that energy was doing was, it was heating up the wood, and wood, or for that matter coal, everything is now we are looking at very heavy and big hydrocarbons. Gas was like methane or ethane, very light. very small hydrocarbon molecular weight wise. Then we looked at liquid fuels, which was C4, C8, C10, C15 type of things. And now we are looking at hydrocarbons which are much bigger, whose molecular weight could reach something like 100,000. So, a very long, complicated hydrocarbon which do not have a fixed formula, and so it is very difficult to write what chemical reaction is taking place. But heating this hydrocarbon, what it does, it breaks it up, and it first releases some very lighter fractions of the hydrocarbons. So, there might be C4, C2H2, maybe C2H6, these type of things will come out after breaking this molecule, and they are the ones which are burning. Then finally, when all of this is burnt out, you can see that this flame is gone, but this then it is glowing, which means that now all the lighter hydrocarbons have been knocked out. There is heavier hydrocarbons which are there, which cannot be converted into vapor phase. They just sit there and they wait for air molecules to come to them, knock it out, and then there is a reaction taking place. So, this is what it gives out, is what is called volatiles, and what is finally left behind and burning is called char burning, and finally, what is left behind after everything has been burnt, which cannot be burnt anymore, we just call it ash, which is nothing but various types of mineral matter which is there in the solid. So, the whole process is now lot more complicated, and to get stable combustion we needed to give lot more energy to this, and this is what makes its burning very, very difficult. Same thing happens with coal, and in a power station or on an industrial scale, to make it burn, we do something else so that it burns and burns faster, which is that we pulverize it. That means we make coal powder, again of the order of mean size of 100 microns, ranging from very small to maybe 200 to 250 micron particles. So, it is a mixture of particles of different sizes. This is fired into the furnace, and what each particle does is that you have a particle there. Coal is not solid or homogeneous, it has got lots of passages in it, and the heating that it takes place, again it releases volatiles. They come out, they form a mixture around the coal particle, and this is where then finally you get a flame, and until all the volatile. So, what is burning out now are the volatiles, and after all the volatiles are gone, this flame will disappear, the char will sit back, and which is heavier hydrocarbons and carbon, then they will keep burning. So, it is lot more complicated to make solid fuels burn. So, now let us summarize and say, well, what have we learned in all of these things? So, what are the observations? That first, we need a fuel and air, but we have not yet answered the question in what ratio. If it goes completely from this to this, for example, we would say that we have a balanced reaction. If it is not, then what? Practically this also happens, and so then we say in both cases, which are the products that will be there. The next thing, and the most important thing we saw just now, is that all chemical reactions or combustion takes place in the fuel in the vapor phase. So, all combustion is that the fuel first has to come into the vapor or the gas phase, mix with air, and then burn, or burn while mixing, both are possible. So, but this is important, whether it is a liquid or a solid, first we have to convert it to a vapor, then only we can look at the combustion process. Then we saw what was the oxidizer. It is air, which is O2 plus 3.76 N2. N2, as we have said, this is not participating, or we can say that this is some inert, but at certain temperatures, to certain extent, it will also participate in a chemical reaction, need not necessarily be exothermic reaction or the one that we are actually looking for. Why? Because if you have this thing burning, a mixture of O2 and N2, and this is at a high temperature, then the reactions will start and we will start getting various forms of nitrous oxides. So, although we will not look at this aspect in this course, the fact is that this is a reason for the pollution that all these combustion process will throw out. We then saw that to start any of these, in all these cases, we needed ignition, which is a certain amount of energy. Gases required less, liquids required a little more, solids requires lot more energy to start. Then we looked at some applications where there was a steady combustion, like what you saw in, say, the gas turbine or the furnace, others which were transient, where it would burn and then the fuel would disappear, then it would come somewhere else, the burning of a drop or the burning of wood and coal. So, this we can then analyze as some sort of a pseudo steady state burning at the macro level. And finally, we also say that, well, what was the, did it happen in a closed system and an open system? In almost all these cases where we needed something to happen continuously, we had to have an open system. So, this gives us a continuous output. And then we came across the idea that there is something called a flame, which is a region where the chemical reaction happens, where the combustion takes place. So, this is what we will now look at. The thermodynamics is now coming to the point where this is important to us. We are going to ignore all the other aspects that we came across in all these applications. There is fluid mechanics issues, there are heat transfer related issues that we will not worry about. We are only going to say we will look at the flame, see what is happening in the flame and try to get some answers to that. So, in the next lecture, we will go back, look at the flame in detail and try to make a simple model to achieve our objective. So, with that we will conclude this lecture. Thank you.